Yeah. First, I'm going to apologise for two things. One, the probably illegible text on the board that I will try and talk through anyway. Secondly, I lost my voice quite recently and it's not actually fully recovered yet. So if I don't sound 100%, that's why. So we're gonna discuss philosophy today rather than quantum mechanics in principle, but it's really philosophy coming from quantum theory, which is a bit unusual, but it's a theorem on free will, which is not a statement you hear very often, but it's really a very minor variation of Bell-Kochen-Specker theorem, which you're more likely to learn if you're doing foundations of quantum mechanics. It was discovered by John Conway and Simon Kochen, two very famous people, in a couple of papers. The first one in 2006, which was subsequently mauled by the entire community, and so they published a slightly better version in 2009, which is still deeply problematic. I'm going to try and illustrate some of those problems there, but their slogan for what free will means is, if indeed we humans have free will, then elementary particles already have their own small share of this valuable commodity. That's their big claim. We'll see later that the way they state it means that claim doesn't really say anything interesting at all, due to problems with their formulation, but there is a non-trivial and interesting way of interpreting the free will theorem, and in that I'm following Landsman's reformulation, and he views this as a no-go theorem for a certain strong interpretation of compatibilist free will. So we won't go into lots of details on the philosophy, but very broadly speaking, there are two attitudes on free will. There's the compatibilist approach and there's incompatibilism. Compatibilism says that free will and determinism are not contradictory. That's the idea, and incompatibilism says they are contradictory. There are lots of arguments for both, and I think these days, given that we believe in quantum mechanics and we believe quantum mechanics is fundamentally non-deterministic, somehow compatibilism is no longer relevant anyway. Reality we don't need to adapt compatibilism to, because reality is not deterministic anyway. However, it's nice to try and see how a much smaller segment of quantum mechanics really allows you to rule out a certain form of compatibilism directly. So let's try and define free will. I know that's a big topic, but very roughly speaking, a simple attitude would be something has free will if it has the capacity to behave differently in the same setup. That's a very, very naive statement. And one issue here already is behave differently. Well, what does that mean? Is there any intention there? Is there agency there, or is stochasticity enough for something to behave differently? And Conway and Kochen don't bother asking those questions. They kind of run with this heuristic definition, and they say they interpret that mathematically in that an agent has free will if the choices they make are not a function of the history of the system as a whole. Which, if you adopt that definition, then stochasticity is an example of free will. So you go back to this slogan, if indeed we humans have free will, then particles already have their own small share of this valuable commodity. Well, that small share is so small that we expect particles to have it anyway, so this statement is not particularly useful from that point of view. So I think we want to, Landsman has tried to address these questions a little bit more carefully. And so he sets the free will theorem up as this no-go theorem for compatibilist free will. So firstly, we need a notion of determinism, and that is essentially there exists this is a determinism. Basically, if we're talking about determinism in the context of quantum mechanics, the claim is there is a deterministic hidden variables model describing what's going on. So there's some state space X. There's a function f from your state space into, let's say, the real numbers that tells you the outcome of your experiment. And because we're going to talk about agents and free will, we're going to add a little bit more. We're going to assume essentially that we've got an agent, Alice, and Alice has her own mental state space describing the kind of choices that she can make. And then there's a state space for the external world. And because the world is deterministic, both Alice's internal state space and the external world's state space can be determined by appropriate functions from our original state. So that's determinism. And I'm sorry that this is a terrible abuse of notation, and I even got it wrong here. But this function that determines the state of the person is some other function of your, with an abuse of notation, it's a function of your internal state and your external state. So that's more or less the idea of determinism in this context. And then freedom is simply the claim that this mapping that takes your state space X to the product space of Alice's internal states and the external states of the world is surjective, i.e., for every possible combination of Alice's internal state and the external state of the world, there is some initial state that allows you to realize that combination. That is to say, whatever the state of the external world is, Alice can make any choice she wants, and that's still a possible state of the world. So that's the key meaning of freedom in this context. And that is a strong form of compatibilist free will, because everything is deterministic. Alice's internal state can depend on the history, it can depend on all sorts of things, but nonetheless, there's nothing restraining Alice's possible choice for any given state of the external world. So that's roughly what compatibilist free will is. Unfortunately, the free will theorem requires you to specify compatibilist free will. We don't just have one agent, Alice, we also have Bob, and Alice and Bob are sharing an entangled state of some kind. But the philosophy is all here, but this is just a setup that says, now we've got a function that Alice and Bob can both determine the outcomes from the original state of the system. Freedom is still given by this surjectivity condition, but we're going to add another property, which is locality, which is the function determining Alice's outcome and the function determining Bob's outcome don't depend on the state space, the choice that Alice, the function that determines the outcome given Alice's choices does not depend on Bob's choice, and vice versa. And we expect that to hold, for instance, if we let Alice and Bob share an entangled qubit in space-like separated regions, and there's no way they can communicate or there's any causal relation between them. Then this final assumption, nature, I've written it in a really bad form because no one can make sense of it if I put it like this. But if you choose the right state in quantum mechanics, these are the predictions. This just says that this realizes those predictions in quantum mechanics. And the free will theorem simply says that these assumptions are incompatible. Incompatible. So you cannot maintain all three of these assumptions at the same time. Given that we more or less believe in locality and nature here, that means compatibilist free will is not on the cards. How long have I If it's 15, I can finish. If it's 10, I can briefly describe the proof. The theorem. But hopefully it's that clear. Sort of.
Would you illustrate one problem when that function you suggest A times E is not surjective?
I mean, okay, a problem that arises is so this relates to the proof. So who knows the Kochen-Specker theorem? Yeah, I better write something down for the Kochen-Specker theorem. So this is morally speaking, anyway. Technically, I can't actually claim this because I've not checked, but morally, it's a corollary of the Kochen-Specker, which is a fundamental theorem in quantum mechanics, which says, incidentally, the Simon Kochen who discovered this is the Kochen of the Kochen-Specker theorem. If you read Foundations of Quantum Mechanics books, you might hear something horrible like it's a no-go theorem for non-contextual hidden variable theories, but what it's saying is we've got a space of observables, Hn, which is just our n by n self-adjoint matrices. And the claim is there is no function V. Can I put the slash the right way? Anyway, there is no function V Hn into R with the following three properties. So quadilinearity, to write everything. So V of alpha u plus eta V equals, that's not now. So it satisfies eta V. Sorry, I shouldn't have used V twice then. So it's linear for all U V in Hn such that UV halos. So for all compatible observables. So it's not generally linear. This is the key point, but it's only linear for compatible observables. It satisfies this dispersion free. I'll use A now. No, I'll stick with U since I began with here. V squared, and it's normalized. So V of 1, that's the identity matrix, is just 1. So no function satisfying these three properties exist. And the idea here is when you can think of this as a function that assigns properties to state, right? And the easiest way of thinking about that is this. You can take this as a projection, so a projection satisfies the total property. And with these 3 points together, well, firstly, by this quantity, any projection has to take V of P is not 1. That's because 1 squared, these are the only thing where x squared equals x. And then any complete set of orthogonal 1D projections by this normalization property, exactly one of those vectors must be assigned a 1 and the rest must be assigned a 0. That means, so given that a projection is basically a state, this function says for any state, yes, the state has that property. If it's a 1, no, it doesn't have this property. It's a 0. And it does so in a manner that's complete. So it's determined by the entire base that you're taking with. And so the non-existence of such a function tells you that you cannot assign properties to states in quantum mechanics. So this is what's known as the non-contextuality. Oh, sorry, the contextuality of quantum mechanics. Instead, whether or not a state has a certain property depends on the entire basis that you're doing the measurement with respect to. It depends on the measurement context, so what you're taking the measurement with. So basically, these properties allow you to say that this function for each external value e, this function will give you will give you a function satisfying these three properties. And that's how you prove that. And in order to make that claim, you really need this to be a variable over this problem, okay? Which is why if it's not projected, it doesn't work. Finally coming back to your question.
The projection, you write P.
Piece by equals P.
Yeah, the P of U squared is P of U squared. So
no, this is for all. It obeys this property for all Hermitian matrices.
also, and in particular, when you put P.
And in particular, when you put P.
Yes, okay.
Any other question?
Space is finite dimensional or
Okay. So because it follows from the Kochen-Specker theorem, this holds in arbitrary dimension greater than 3. N must be greater than or equal to 3. In 2D, it holds. You have characteristics. But yeah, infinite dimensional does work because you can just restrict the 3-dimensional subspace if you're running.
Sorry, when you said the three properties are contradictory, you mean all three, or is it possible for two of them to be not contradictory?
Yeah, I think you can probably take any 2 out of 3 and cook up a bunch. I've not checked. I think you need all 3 to get a contradiction.
Okay, so it's possible for 2 of them to be compatible.
Once you assume these 2, then you get predictions that don't align with the predictions of one.
Well, so that the Kochen-Specker theorem is a very mathematical statement. So how does it have something to do with the very philosophical free will?
No, so it's just the way you prove it. So Kochen-Specker is mathematical and to do with foundations of quantum theory, but
Okay, so then why does it have something to do with quantum theory?
So you can think, so these are your observables in quantum theory. And you're trying to say this function is really something that assigns properties to measured quantities in quantum theory. And it's quite, when these assumptions a priori don't look particularly natural. Okay, normalization, you just assume it's finite and then you normalize, so that's not a big deal. But if you think about it, quasi-linearity is not so far because when they commute, these are compatible observables. So then you can do a simultaneous measurement. You can find the joint eigenbasis of the 2 observables, do a simultaneous measurement, and then it's not so surprising if linearity holds.
So if you restrict the argument to the diagonal, so mutually commuting subspace, then you can find such a function Z. It seems
I mean, this Kochen-Specker theorem says such a function does not exist.
Oh, well,
Satisfying all 3.
I'm asking
yeah.
Oh, well, but the second, condition V U square equal U square is that's for any matrix U.
Yeah.
So my question is that if where that condition is satisfied only for diagonal part, then is there such a function V where it seems
I mean,
to me that there's no
when you do because this is self-adjoint, we can always
yeah. But first, what happens?
No, but you're just looking at the. I think this should be independent of the diagonalization.
Yeah. But my question is, what happens if, well, you just
C
consider
times the identity.
yes, yeah.
That's about yeah, such a function exists. Yeah, because that's just the classical function.
Yeah, but
I mean,
doesn't have the well, but the first condition can be satisfied simultaneously with the second condition.
Well, not in dimension 3 or higher. But if you restrict to the diagonal, then you're just going to one dimension. That's fine.
Well, not one dimension. Well,
Yeah,
so
effectively you're restricting to, you're making the same claim for R. No.
Well, you want to pick some orthogonal basis of H.
yeah.
If you do so, and only if you only assume this second property for such orthogonal basis, then he claims, and I agree that there are such functions.
Oh, I see.
I don't understand. Suppose it's a sort of the expectation value of U square or something, then it cannot be true in quantum mechanics, right? So what is the second assumption about what? Is it natural or?
So okay. It's not, let's put it this way. If we think of V as, we might, because V is a kind of objective assignment of a numerical property to states, we might, I think it's quite natural for any suitable function, or at least polynomial functions, to satisfy this commutation relation. That would be a natural thing to say if properties are satisfied. So, because we're just saying that this assigns an objective value to something in a particular state. This takes a function of that state, and so on. This was held in classical mechanics, and then this is a particular example of that. But it's not. It doesn't work in quantum theory.
That means no variance.
Yeah.
Classical.
Yeah. No. The attempt is to interpret quantum theory in a classical way of the theory.
Yeah, so it's classical.
Yeah. This is classical. This is natural from a practical point of view because you're assigning objective properties, states and things, but that can't happen in quantum theory. So this is an example of why quantum theory is different from classical. If you want to look at it.
Yeah, any other question?
So, what does that leave us? So what's the kind of summary?
Okay. Okay, I mean, I think this is about fundamental physics, and whether free will has anything to do with what's going on at the particle level is dubious to me.
Really? But
Yeah.
you follow? Aren't we particles?
Yeah, we are, but I mean, my view is free will is some emergent thing that you have to deal with at the level of let's say mental processes, but whether random processes at a particle level have anything to do with that is not clear to me. Now, you could quite happily still maintain an incompatibilist point of view, and since we don't believe that the world is fundamentally deterministic, quantum mechanics is somehow opening up a space for incompatibilist free will, an incompatibilist approach to free will. I think it does mean that the very, if you really want to say that the world is deterministic, and you want to maintain this strong notion of free will right up from the particle level, let's say, or right up from quantum processes to mental processes, then this statement says you cannot do that. So you have to give up determinism or free will, or locality.
Sorry, just to make sure, so the demonstration is making use of quantum mechanics, or is it just, yeah?
Well, I mean, this
Because you
is
assume the
fundamental.
state of the system is described by a vector and a
Yeah. So nature, I've not written it, but this is basically saying you've got Alice and Bob. Alice and Bob are both making a choice of basis measurement for some spin, for a massive spin one particle, in three-dimensional space. And you choose a state in such a way that their measurements are perfectly correlated, like a GH. Well, it's not a GHZ state. I can't remember what state you would choose, but you choose some appropriate state, and these properties all hold.
Okay, so determinism in this context means the determinism of the evolution of this.
No, determinism is a separate statement about the existence of essentially a hidden variable model, a deterministic hidden variable model for
Just to make sure, so any stochastic process cannot satisfy this free will theorem, or
No, this one no. The Conway Kochen one, yes, as far as I'm concerned. I mean, they don't write or define anything, which is, given that John Conway is a mathematician, it's an unusually, it's a paper lacking in rigor, let's say, even from a physics standard. And as far as I'm concerned, there's nothing about their definition which means a stochastic particle would not be free. So then their whole claim is, fine, fair enough. I bet that at the same time, they did notice that you could use quantum mechanics to talk about free will, which no one else had pointed out before. Fine. So it was definitely inspired in many ways, but go and try and read the 2006 and 2009 paper on free will and strong free will theory. They're not particularly clear.
I find it interesting that you separate free will from particle, because, what about AI?
I'll put it this way.
Make that distinction.
I've got a terrible humanities upbringing due to my parents, and I'm a Kantian, so free will is an axiomatic necessity in order to identify moral subjects from my point of view, and then you build up from there. And I think there's enough space due to emergentism for that to be the case. So this is not. I have no science on free will. Other than this, I've got a, that's just me. Okay.
So you mentioned that according to Conway and Kochen, history choice is not a function of the history.
Yeah.
Does this say anything about what kind of function that was?
No, they just mean a function, an ordinary mapping. But they don't tell you what the history is. They don't tell you
what it maps to.
Yeah. Presumably they have some kind of space of choices which will be modeled by a parameter space, or like the space of bases that Alice can choose. I think they do implicitly. They just don't bother saying. At least not in the strong free will. The second paper, the first paper, I don't remember. I've not read it in a very long time.
Because if you can map history to, for example, a probability distribution.
Yeah. But that would be free will. In that the probability distribution will give you different choices. So it's not very. I don't think they're very clear about what what they mean by free will. Conway and Kochen.
Okay, any other questions or comments, discussions? Okay, let's thank Christy for this provocative talks. Thank you very much.